So now that we've seen Bloom filters and we've seen how to insert items, how to query, we've seen that it's small, we've seen that it gives false positives, which is to say sometimes it'll say that the item is in the set when it's really not. Now we want to really analyze how often does it give false positives. And given false positive, that it has a false positive rate, how should we design the filter? For example, how many slots it should have or how many hash functions it should have so as to achieve good false positive rates. So let's say we've got a Bloom filter with n bits and that's using k hash functions. And let's think about what is the false positive rate of this Bloom filter given a data set where we're adding m items, m distinct items. Let's assume that the hash function has the properties we would like it to have, so it spreads the items evenly across the buckets of the Bloom filter, the slots of the Bloom filter, and the k hash functions are independent of each other. So the assignment given by hash function 1 and the assignment given by hash function 2 are in no way related. You can't predict one based on the other. And so here's the first question related to false positive rate. What's the probability that a given bit in the filter is 0 after we've inserted m items into the Bloom filter? So for example, without loss of generality, let's just pick one of the positions in this Bloom filter. Let's pick the first one here. And let's say that's us. We are slot number 1 in the Bloom filter. And so the first thing that we can write down is, let's say an item's being inserted, and let's say there's only one item and one hash function, or let's just limit our attention to one item and one hash function. So there's only going to be one hash value generated and only one bit in the Bloom filter being set. So if I'm a particular element in the Bloom filter, what's the chance that I'm the one that gets picked by that hash function? Well, there's n slots and I'm just one of them. So the chance that I would get picked would be 1 over n. And to flip that, what's the chance that I wouldn't get picked, right? Because we're saying what's the probability a given bit is 0. So that's a statement about whether I don't get picked. So what's the probability that I don't get picked? Well, it's just 1 minus that. But that was the scenario if there was only one hash value, if there was only one time when we produced a hash value. But we're adding m items, and there are k hash functions being applied to each of those m items. So really, the number of times that I might be chosen is m times k. So if this now is the probability that I'm not chosen one time, the way I would write down the probability that I'm not ever chosen, even after all those m times k attempts, would be to write mk up here in the exponent. Okay? So that's the probability that a given slot in the Bloom filter is still set to 0 after I've inserted all m items in the input. Okay? I'm also going to call this p sub 0. So here is the definition of p sub 0. It's the probability that a bit is still set to 0, or you could also think of it as the fraction of bits that are set to 0. Our expectation of the fraction of bits that are set to 0. Okay, so if that's the expression for p sub 0, the probability that a bit is 0, well, the probability that a bit is 1 is just going to be 1 minus p sub 0. There's only two possibilities. I'm either set to 1 or I'm set to 0. So what we have here is the probability I'm still 0. If I wanted to know the probability that I got chosen one or more times by those m times k hash functions, then that would be this, 1 minus p sub 0. Okay, now let's ask the question about the actual false positive rate, the question we set out to ask. What's the probability of a false positive? And remember, what we mean by this is if we are asking whether an item is in the set and the item is not truly in the set, it's not one of the ones that was used to build the Bloom filter, then false positive would be if the Bloom filter had ones in all k positions, all the k positions pointed to by our k hash functions. So what's that probability? So it's a coincidence of finding a 1 k times. So that's just going to be probability that the bit is set to 1 to the k, right? That's the probability that all k of the places that I look are all set to 1 just by coincidence, just from collisions, okay? And of course, because we know p sub 1 is 1 minus p sub 0, so we could also write it this way, which means now we can rewrite it plugging in p sub 0, plugging this in. Now I'm going to write a larger expression, so I'm going to have outer and inner parentheses. So let's start with the outer, 1 minus. Now for the inner, which is p sub 0, 1 minus 1 over n to the mk. And then don't forget, I now have to end the outer parentheses and put this k up in the exponent. So that's the expression for the false positive rate. And in blue, I've highlighted the fact that the sort of kernel of the false positive rate is this expression for the probability that a bit is set to 0 after all the additions. And you could even say that inside this probability, there's kind of a core of just the 1 minus 1 over n, which is the probability I don't get picked by a particular hash function. So here's our expression for the false positive rate, and for short, we'll call it f. So we've got these two expressions, probability that a bit is set to 0 after all the additions, and false positive rate. Where do we want to go next? Well, I would observe that this expression for the false positive rate is really pretty complicated, right? So it's got n in there, it's got m in there. They're not together, right? They're in two different places in the expression. And it's got multiple places where k appears. So k appears here inside the outer parentheses and here as an exponent to the outer parentheses. Okay, so that's a little tough to work with. We want to be able to do things like pick the best k, and that's a little bit hard the way this thing is phrased. There's sort of two competing k's, and in fact, one of the k's has the effect where as k grows, it's reducing the false positive rate, right? The k up here, if you held everything else constant. One of the k's is having the effect of increasing the false positive rate. This one in here. So what do we want to do next? We would like to simplify this expression. So it's a little bit easier for us to do things like pick a good k, or pick a good n, a good number of bits in the Bloom filter. So what we're going to do next is we're going to look at approximations of this false positive rate expression. Well, an approximation of this expression and this expression that uses e. We're going to look then at a strategy for choosing k once I have fixed the other two variables, m and n. We'll look at some ideas for how we might want to fix m and n. Well, actually, we generally don't have control over m, but we might have control over n. And so some strategies for how we might want to do that. And then we're ultimately going to move on to using the balls and bins strategy to think about what are the scenarios when we are close to these ideal conditions, the ideal k and n given m. And that's where we can start to bring in some of these special cases of balls and bins, like coupon collector. Okay, let's start by taking our expression. This is p sub 0, right? This is the probability that a bit is set to 0 after all the additions. And let's find a way to rewrite it that's hopefully simpler. And we're going to use an approximation on the way to doing that. So the idea to start with is that we're just going to rewrite it so that we have e to the something. So I'm going to put square brackets here, e to the something. And that e to the something should be equal to the original expression. All right, so what do I have to put in the exponent? I have to put the natural log of that expression. So let me put ln of 1 minus 1 over n to the mk. So what I have here is of the form, e to the natural log of x, which is just x, right? So this expression here is this expression, but rewritten. All right, why would I do that? It's a little odd, but you'll see in a moment. So one thing I can do, one immediate benefit, is I can take the mk and put it sort of out in front. So let's now write mk natural log of 1 minus 1 over n. And now in this expression, things are starting to look simpler. I've got e to the mk. The tricky part is this part, the natural log of 1 minus 1 over n. If we could make that simpler and it turned out to be a simple function of n, then we would have a pretty good expression at the end of the day. We'd have e to the m times k and then hopefully some simple function of n. So how do we attack this natural log of 1 minus 1 over n? We try to approximate it. And how do we approximate natural log of 1 minus 1 over n? Well, it looks a bit like the function, f of x equals natural log of 1 plus x. It's just that in our scenario, x is minus 1 over n. And it turns out that natural log of 1 plus x is a function that has an easy Taylor expansion, an easy to work with Taylor expansion. In fact, it's sometimes called the Mercator series, and it looks like this. So this is the Taylor expansion, again, of natural log of 1 plus x. So it's a series that is x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4, etc. So we have alternating minuses and pluses. We, of course, have x's exponent going up. And so in our scenario, though, x is minus 1 over n. And what's n? N is the number of bits in the Bloom filter. And so the Bloom filter might have many, many bits. N could be quite large, right? We could have a Bloom filter that's a kilobyte or a megabyte or a gigabyte. But let's just stick with a kilobyte. So let's say a kilobyte, let's say about 1,000 bytes it's 8 bits per byte, so that's about 8,000 bits. So that would, even a kilobyte Bloom filter would have 8,000 bits. Let's just say, for simplicity, that n is 1,000. So we have 1,000 bits in our Bloom filter. All right, then of course x is minus 1 over 1,000. And we can plug that in to the x's in this expression to get some idea. What we're trying to get at is how many terms of this do I really want, do I really need? Okay, so let's say, all right, so that x becomes minus 1 over 1,000, minus 1 over n, which is minus 1 over 1,000. Then we get minus, but I've got this, so I've got this x squared in the exponent, so that's going to be minus 1 over 1,000 squared. I'm going to get minus 1, or I'm going to get 1 over a million. All right, so I'm going to end up with minus 1 over 2 million. Okay, that's this term. Now for the next term, I've got x cubed in the numerator, so that's going to be minus 1 over 1,000 cubed. That's going to be minus 1 over a billion. So I'm going to end up with minus 1 over 3 billion, etc. It's going to be minuses all along when we plug in a negative number. Okay, so let's just rewrite. We could also have written 1 times 10 to the 3 here. If we just look at the exponents, we can see obviously that these fractions are getting very small very quickly. We've got 1 in 1,000, 1 in a million, approximately 1 in a billion, approximately, right? So it's decaying very quickly. Okay, so if we wanted to decide which of the terms do I need, and we were interested in precision out to, say, the thousandths, but not so interested in precision out to the millionths, well, then we could just stop here. We could just take the x and ignore everything after that in the Taylor series, okay? Which would give us a very simple approximation, right? Our approximation for natural log of 1 plus x is just x. So that's what we're going to do. So imagining x to be a small number, like 1 in 1,000, terms beyond the first are going to be just really small, like less than a millionth. So we can just go with that first term as our approximation. So that means our approximation for natural log of 1 minus 1 over n is that it is approximately minus 1 over n. And plugging that back into our expression with e, that means we think this is approximately e to the minus mk over n. And this now is a pretty simple expression, right? We've got mk and n all in a simple function together, a simple relationship together in the exponent of e. Okay? So here's, again, our expression for p sub 0. We just came up with an approximation for that. So now here's wavy equal sign, since it's an approximation, and here's our approximation. And we'll just call that tilde p sub 0. It's an approximation for p sub 0. So the false positive rate, which of course can be written in terms of p sub 0, we can plug in the approximation for p sub 0, tilde p sub 0. And this we might say this is what we would call tilde p hat. Okay? And in this approximation, let's just write it again, and I want to highlight that we can sort of take the m over n part and separate it from the k. And that m over n sort of has meaning in itself, right? The m over n is the number of items divided by the number of slots in the Bloom filter, right? That kind of has some meaning, right? It could be that under many circumstances, there's a ratio that would be pretty good, an m to n ratio that would be pretty good. Like you might imagine, for example, maybe 1/2 would be a good ratio, 2 bits for every input item. Right? So m over n is a quantity that seems to have some meaning in itself. It makes sense to think about taking m over n and let it be fixed so that we can study k. Okay? So let's now study k. We want to study the question of how do I pick the best number of hash functions, right? And we kind of know, maybe intuitively, but let's say this again. We know that we can pick too many and we can pick too few. So what would it mean to pick too many? Can we have too many hash functions? Well, for example, let's say that k was so high, it was approaching n, so the number of hash functions was approaching the number of slots in the Bloom filter. Okay? So even just adding one item would set many, many, many of the bits to 1. And so it wouldn't take too many items before the Bloom filter was very clogged up with many 1s. And therefore, we were going to get lots of false positives. We would have a high false positive rate, basically because the fraction of set bits was quite high. So here's our expression for false positive rate in terms of the fraction of set bits. Essentially what we're saying is that this base, this p sub 1, is going to be so close to 1 that it doesn't matter so much that we have k in the exponent. The thing we're exponentiating is so close to 1 that we're not getting rapid enough improvement. So that would be one scenario. Can we have too few? Well, yeah, right? The whole point of having repeated trials was that if we only had one hash function, we would be stuck with whatever the original false positive rate was. Whereas if the false positive rate were 1/2 and we chose k appropriately, we could drive down the false positive rate. We want the repeated trials in order to exponentially drive down the false positive rate. Okay? So if we picked too few hash functions, the problem would not be here in the base, right? P sub 1 would now be reasonable. It would be small, in fact. The problem would be that the exponent wasn't high enough to get enough driving down action. It wouldn't be driving down the false positive rate fast enough. Okay. So here's the false positive rate again with the approximation in here. And of course, we've got these two k's corresponding to those two extremes from the previous slide, right? If k is too large, then the problem here is that this becomes really close to 0 and the whole base becomes close to 1. If k is too small, the problem is we don't get enough benefit from the repeated trials, right? The exponent is too small. So if I were to draw what the function looks like, vaguely, what the function looks like, where I've got k here, and I've got the false positive rate here, well, we know we can be too high, and we know we can be too low, and we know there's probably some sort of happy medium in the middle, where, k too low corresponds to, not enough trials, and then k too high corresponds to clogged filter, right? Too many 1s. But we think there's a sweet spot in the middle. So how would we find it? Well, we seem to have a function that has a minimum, and at that minimum, if we're holding m and n, or m over n, if we're holding m over n fixed, and considering this to be a function of just k, we could say, well, let's take the derivative of the function and see where the derivative is 0, and that's going to tell us where that minimum is. And you can do that. It's a little laborious. I'm not going to show it. It's because this is a complicated composition of functions here, so we're going to be doing lots of chain rule, product rule type stuff. One quick tip would be, if you were going to start, you could take the log, and that would yield a function that has the same minimum but was a little bit easier to work with. But what you would find is that the derivative is 0 when k equals this quantity here, which involves n over m. That's actually the flip of the fraction that we were looking at before. So n over m, which is kind of like bits per item. Okay. And this is the ideal choice for k for that n and m. It's the best choice for k, called k star, given that n and m, or n over m, given that n over m. So as an example, let's just look at a picture. Here, let's say we said n over m was 10, and here is false positive rate, and here is our curve. I actually only evaluated it really at the integer values of k. The true curve would look a little different from this. If I evaluated it everywhere, it would have its minimum right here. So this part would be like sort of like that. And so k star says that the best choice of hash function is 6.93, so between 6 and 7. And so we could try rounding it up and rounding it down and see which one yielded the better value in terms of false positive rate, and we would see that 7 was the best. So we would pick 7 in this case. Okay, so we have a way of picking the ideal k for a fixed m over n, or n over m. One interesting question we can ask is, if we do pick the ideal k, what does that tell us about the fraction of bits in the filter that are set to 1? We know it's not all of, it's probably not all of them, because that would not be a low false positive rate scenario. We also know it's probably not that very few of the bits are set, because again, that would seem to indicate that we could have driven k up higher and got more benefit out of repeated trials. So what exactly would it be? This is not so hard to figure out. So let's just write down this expression that we already know. This is just the definition of tilde p sub 0. So we're using the approximation. So we can manipulate this a little bit to solve for k. So we might, for example, just take natural log of both sides. Right, and then multiply both sides by minus n over m. So we'll end up with minus, let's put the minus out there, log p hat n over m. Okay. And so that's just a way of saying what is k in terms of n and m and p0. But it mirrors what we wrote down for k star, right? It looks like k star a little bit in shape, in sort of form. What was the expression for k star? It was natural log of 2 times n over m. So we've got these two expressions. The difference is this part. But we can set the two expressions equal to each other to figure out what is the tilde p sub 0 that we get when we pick the ideal k, when we pick that particular value for k. And that's not so hard to do. We just set these equal to each other, and we end up with tilde p sub 0 is 1/2. In other words, when we choose k optimally, we end up with a filter where half of the bits are set and half of the bits are unset, which is kind of a nice result and a nice way of thinking about it. If we are going to probe the Bloom filter to try to figure out whether an item is a member of the set, in some sense we're getting the most information if the most membership information from the filter if the filter is about half zeros and half ones.